All right, now let's get into quantum mechanics a little bit. So, in quantum mechanics, there's something called the wave equation, and we use the Greek letter psi to indicate the wave equation. And when you square this wave equation, you get what we call a probability density map. It's this three-dimensional plot of where you're likely to find the electron. So where this is darker, that's where you're more likely to find the electron. All right, where it gets lighter out here, you're less likely to find the electron. You're way less way out here. So this just kind of shows you where it's most probable that you're going to find the electron. There are multiple solutions to it, so this would just be one of them. When you solve the wave equation, you get a full set of orbitals and their corresponding energies. So you set of wave functions or orbitals. These orbitals are basically clouds. So sometimes you'll hear them referred to as an electron cloud. It's a three-dimensional shape where the electron lives. Sometimes I'll even call it a balloon animal because they look like little balloon animals. There's different shapes to them. All right. So an orbital is described by a set of three quantum numbers, and I'm going to tell you about those now. And also, while I'm mentioning it here, there are four quantum numbers total. The first three are talking about the orbitals. The last quantum number actually talks about the electron itself. So let's get into the first three quantum numbers. All right, there's something called the principal quantum number, and the symbol for the principal quantum number is the letter n. It's a lowercase n. N tells you the energy. All right, so there's different energy levels. Remember in the hydrogen spectrum, you saw those different lines. It's because there are different energy levels in atoms. All right, N tells you what the energy level is. Now, if you're a scientist and you're going to start numbering energy levels, what would you call the very first energy level? I'd call it number 1. And that's what they did. So the first energy level is 1. The second energy level is 2. Third one is 3, and so on. So the values of n are going to be integers that are greater than or equal to 1. Very easy. So far, so good. All right, our next quantum number is L. All right, that's a lowercase kind of cursive L. It's the angular momentum quantum number. Sometimes they'll call it the secondary quantum number or azimuthal quantum number. It's got a couple weird different names to it. But this quantum number tells you the shape. So not all these electron clouds are going to have the same shape. All right, so L will tell you the shape. L depends on N. All right, so the values that you can have for the angular momentum quantum number, they depend on what value of N you have. All right, so L always starts at 0 and goes all the way up to 1 less than whatever N was. So for example, if N equals 2, L could be 0 or 1. If N equals 5, L could be 0, 1, 2, 3, or 4. If N was 20, let's go crazy here. If N is 20, L could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it goes all the way up in integers to 1 less than N. All right. We also use letter designations to talk about the different values of L. So, I mean, granted, like L's a letter, but we use letter designations for the different values of L. So let me just show you that on the next slide here. So if L equals 0, that's an s orbital. If L is 1, that's a p orbital. If it's 2, that's a d orbital. And L equals 3 is an f orbital. Right? There are no known elements that actually have electrons in anything past the f orbitals. However, if we do eventually make something, because we're always crashing stuff together, the next one would be G after that, and it goes alphabetical F. So you have F, then G, then H, then I, and so on. But those would be really unlikely to ever see in your lifetime, if ever. It gets kind of crazy. So S, P, D, and F, 0, 1, 2, 3. I used to sit there and just say that over and over again, like 0, 1, 2, 3, SPDF, 0, 1, 2, 3, SPDF, to lock it in my head, those different values. But these different orbitals all have different shapes. And I'll get to that in a video after this one. All right, so that's that quantum number. The third quantum number that talks about the orbital is the magnetic quantum number. That's M sub L. So it's an M with a little subscripted L. So we call it M sub L. And this tells me the orientation, right? The direction. So some of these orbitals have kind of a direction to them. They can be pointing up or left or right or forward or some different direction. This is going to tell you kind of the direction that the orbital is pointing in. Now, just like L depended on N, M sub L depends on L. So these are all kind of snaggled in here. So the allowed values of M sub L, they're going to be integers, and it goes from negative L all the way to positive L in integers. So what the heck am I talking about? All right, so let's say, for example, L equals 2. If L equals 2, your M sub L values could be -2, -1, 0, 1, 2. If L was, let's say L was 5. So if L is 5, M sub L could be -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and 5. So it goes all the way from -L to positive L in integers. All right. Well, I'll do some more stuff because I know right now you're probably watching this going, oh my gosh, craziness. All right. When you have your atom, right? This part of Bohr's model we still definitely keep. There are energy levels for sure. N equals 1 is the first energy level, right? N equals 2, second energy level, N equals 3, and so on. So these are your different energy levels. The higher the energy level, the further you are from the nucleus. Remember, the closer the electrons get to the nucleus, the lower their energy gets. So these are higher energy levels out here than in here. It wants to be low energy. So your principal quantum number, like this 1, 2, 3, 4, this will correspond to the periodic table, and I'm going to show you that later in this chapter. It's kind of cool, but there is a definite connection to the periodic table. All right. Last slide for this particular one. You can calculate how many electrons go in each shell. So as you can probably guess, these are spheres, right? That first sphere is the smallest, and then the second sphere, it gets bigger, and they get bigger and bigger. And as you might guess, the electrons, you can put more and more electrons in the bigger and bigger spheres, right? So how many electrons can you put into a shell? There's an equation for it. So 2n squared. So n is your principal quantum number. This is the energy level you're on. So how many electrons can go into the first energy level? 2, right? How many can go into the second energy level? So you put in 2 for n here. That's 8, and so on and so on. So this is a handy equation that you can calculate how many electrons can fit into the energy levels. Now, the electrons are in the outermost layer, the ones with the highest principal quantum number. Those are what we call the valence electrons. All the ones below it are kind of inside the atom. Those are what we call core electrons. The valence electrons, as it turns out, are going to be the really important ones because those are the ones that interact with stuff. Those are the ones that are on the outside of your atom. Cool? All right. Hang in there. You can make it. You can do it. We're getting there. All right. See you in the next video.